Hello, this is section 1.2, or at least I'm going to do as much of it as I can. After I looked at it, it's going to be more longer than what I plan to do in one lesson. So I'm planning to break it down into two parts and stop after the end of Roman numeral 1. So today's lesson, we're only going to talk about the metric system, and we'll save scientific notation and below there for the next lecture. So also you'll notice it's in a different format. So I'm going to be playing around with different things until I find a way to do my lectures and post them that I like better. So anyway, so getting started, we're going to talk, we're all familiar, we grow up learning about the imperial foot-pound second system, or also known as the English system. But science is mostly in the metric system. So we're going to become familiar with those units. So a system of measurement is a collection of compatible related units that can be used to measure quantities such as length, mass, or volume. Now, the imperial foot-pound second system, I'm sure you're very familiar with inches and feet and quarts and pounds and all those things listed there. But we're going to be talking about the metric system, or the SI, and that includes the meters, liters, grams, hectares, seconds, Celsius, Kelvin, and several others. But we're primarily going to focus on the first three: meters, liters, and grams. So just out of curiosity, do you have any idea in all the world how many countries do not primarily use the SI/metric system? So if you guessed 3, you're correct. So here we've got us, the United States, Liberia in Africa, and Myanmar or Burma in Southeast Asia. Now, even though in the United States, they legally authorized the use of the metric system ever since 1866, yet we always use the foot-pound second system. So it just keeps on being the most commonly used thing. So it would be way simpler if we just learned the metric system all the way from day one, and then we'd all know it inside out. But anyhow, we're going to talk about meters, liters, and grams, and these are what we call the base units. So see on this chart, there's all these different prefixes, and the base unit goes right here in the middle, and it's the one unit. Now, depending on if you're looking at small things or big things, or measuring small things or big things, you go up on this chart if it's smaller. And the beautiful thing about it is that each unit is different from the previous one by a factor of 10. So it's kind of like the decimals. It is the decimal system. So here we've got the base unit right here. So let's say it's a meter, and a meter stick you've seen has centimeters. So centi means hundredth. So it's been divided into 100 equal units. And if you look at each centimeter, it's broken down into 10 more little marks, little hash marks on there. And that each one of those is a millimeter. So all of the way up, each one gets to be a factor of 10. It's smaller by one factor of 10. And then likewise, if we go down on this chart, each one of these is bigger by a factor of 10. So a kilometer or kilometer is equal to 1,000 meters. So here are our prefixes again, and this page is just about different meters. And prefixes of meters to become kind of familiar or more familiar with what sizes each thing is. So over here is a meter stick on the bottom with a yardstick on the top. So a yardstick is just ever so slightly shorter than a meter stick. It comes in at 91.4 centimeters, whereas the meter stick is 100 centimeters. So it's 8.6 centimeters short. So that's a little over 3 inches too short. A doorknob handle right here is usually they're about a meter off the ground. So you can visualize how tall that is. Now up above that is a penny right here. So a penny is approximately 1 centimeter wide. Eeks. And each one of these little marks in between is a millimeter. So here it is between the two blue arrows over here is 1 millimeter. Now going small by a factor of 1,000 times smaller than this millimeter is a micrometer. So it's 10 to the negative 6. That means it's 0 point with 6 decimal places to the right. So this red blood cell right here, the thickness of it is 20 micrometers or microns thick. Here's a piece of hair. So the hair on our head, 50 to 70 micrometers or microns in diameter. So all the way across the circle, you know. Here's a piece of sand. If you went to the beach, 90 micrometers, each little grain. If you look at the tip of your pencil, 200 micrometers thick. Okay, now if you, so that's a million, a micrometer is 1/1,000,000th of a meter. Now a nanometer is a billionth of a meter. This meter stick, if you cut it into 1 billion equal pieces, a sheet of paper is 100,000 nanometers thick. So you know how thin a sheet of paper is. Okay, now talking about bigger things. So the meters, how tall a doorknob is, a decameter, DA meter, is equal to 10 meters. So if you think about how long a school bus is. Now a kilometer, now decameter is not used very often. A train is a long train. You know, you wait at the train crossing and you have to wait several minutes for the train to go all the way across. So you can, so the little levers are raised up and you can cross. So trains are often 1,000 meters or 1 kilometer long. And the state of Alaska is approximately 1 megameter or megameter wide. So a kilometer is 1,000 meters. A megameter or is 1,000,000 meters. All right, now talking about liters. So everybody knows what a 2 liter of soda, how big that is. A liter is just slightly larger than a quart. So a gallon doesn't quite have 4 liters. It's got 3.785 liters. Now, the water bottles that we buy, that we drink out of a lot, like this Nestle water bottle, it has a 1/2 liter or 500 milliliters. And then if you take medicine or a syringe at the hospital or something, it is measured in milliliters or cc's. And you might note that 1 milliliter is equal to 1 cubic centimeter. So a centimeter but times a centimeter times a centimeter, like a sugar cube or something, or it's abbreviated cc for cubic centimeter. So a bathtub, a typical bathtub holds about 50 gallons of water, and that translates to 189.3 liters. So that gives you some ideas about liters. And grams. Grams are what we use to measure mass or weight. This paper clip, or a paper clip, generally weighs around 1 gram. And if you take Tylenol or Motrin or some other kind of medicine like that, most of them are like 500 milligrams or something, which is 1/2 or 0.5 grams. If you go to the store and buy a pineapple, it's about 1 kilogram. 1 kilogram is about 2.2 pounds. And these elephants over here, the male Asian elephant has the tusk and it's bigger. They weigh around a little over 12,000 pounds, which is 5,500 kilograms. And a female Asian elephant weighs around 7,000 pounds, which is a little over 3,000 kilograms. So you can see how much each of those amounts are. Or if you like cars better, so here's a 2020 Toyota Corolla SE, and it says it weighs 3,110 pounds, and that is equal to a little over 1,400 kilograms. So I don't know if you've studied about the difference between mass and weight yet, but weight is, it takes into account the force of gravity, and mass does not. It doesn't matter if you're on the moon or if you're standing on the earth or if you're on Jupiter, or where you are, what kind of mass, what the gravitational pull of wherever you are. It's strictly how much, the amount of matter that is present in an object. Now, weight always takes into account the force of gravity. So on the top, I've got two pictures of two scales that can measure mass because they can cancel out the effect of gravity. Since it's got an arm on either side, it's here's an egg on this side, and it's got the weights on the other side, and gravity is pulling on both sides equally, and so we can cancel out gravity and it only leaves the mass. So this egg is the equivalent of 60 grams, and if you did this on Earth, or if you did this on the moon, or if wherever you were, it would still say that that egg was the same mass as those 60-gram weights are. Now, on the top right hand side is a triple beam balance, and that's what we're going to use in our lab, in our next lab. It's got weights on the right hand side that you slide over to make it balance with whatever's on the pan on the left hand side. So again, it's very similar to the balance on the left hand side. You just the gravity is pulling on both sides, but since it's pulling on both sides equally, you can cancel it out. So it only leaves the mass, and that would be the same wherever you were. But now the scales on the bottom, like the first one is one like you see at the grocery store that you weigh your bananas on or something. So it doesn't have a place to cancel out the gravity. It's only got one place on the top, and gravity is going to be pulling on whatever you're weighing as well as the mass. So and the same on the bathroom scale, like that we stand on to weigh ourselves, and the food scale on the right. There's no place to, it needs to have two places to have, it needs to have one place where you're weighing something and the other place where you have weights to balance it with. So these three on the bottom don't have that, so they can only measure weight. Okay, so now density, since we're talking about mass, density is defined as the mass per unit of volume. Um, it's how tightly things are packed together. The atoms in the substance, how tightly they are packed together. Now, water, right here. So at room temperature, and of course, the density changes depending on what temperature it is. But at room temperature, which is somewhere between 20 and 25 degrees Celsius or 68 to 77 degrees Fahrenheit, the density of water is 1 gram per cubic centimeter. And remember, 1 cubic centimeter is the same as 1 milliliter, or 1 cc is the same as 1 milliliter. So water is really nice that 1 cubic centimeter also weighs 1 gram. So that's a very handy thing to know. Now, over here, we're talking about how dense something is. So on the left-hand side, it shows a gas, and see how spread out the atoms are of the gas in the air. And then in the middle, they're a little tighter together, and the solid, they're packed right against each other. So the solid is much more dense than the gas, and the liquid somewhere in the middle. Now here's a bunch of different substances. This is figure 1.6 in your book, and it shows all of these things that weigh, or their mass is exactly the same. They're equal masses or equal weights of these items. So we have 1 kilogram of air, 1 kilogram of cork, a kilogram of pine, wood, a kilogram of water, glass, marble, aluminum, iron, lead, and gold. Okay, but they're all different sizes. So this gold, the 1 kilogram of gold, that's the one that's the most dense. And of course, the air is the least dense. So it's a giant cube of air. It's cut off even, so we don't even know how big it is. But anyhow, density is the mass, how much something weighs, divided by the volume, how much space or space that it takes up. All right, now Celsius. So we're used to Fahrenheit temperatures probably, but I'm sure you've learned some about Celsius. So 212 degrees Fahrenheit is what temperature water boils, but 100 degrees Celsius is the Celsius temperature that it boils. And water will be a gas at any temperature higher than those temperatures. Liquid water is liquid any time between this temperature and anything under 100 degrees Celsius down to above 0 degrees Celsius. So I put 1 to 99 degrees Celsius is water, or 33 to 211 degrees Fahrenheit. Now, frozen water or ice, water will freeze if it's below 32 degrees Fahrenheit or below 0 degrees Celsius. So anything below there will give us ice. Now we need to know how to convert between temperatures that are given in Fahrenheit and change them to Celsius temperatures. Or maybe we have a Celsius temperature and we need to know what temperature that would be in Fahrenheit. So I've worked out examples over here using the formula. The formula is on the white bar, and plugged in convert 212 degrees Fahrenheit to its Celsius temperature. So Celsius is equal to, parenthesis, the degree Fahrenheit minus 32 degrees Fahrenheit, and then multiply that by 5 degrees Celsius over 9 degrees Fahrenheit. So here down, So here we go. So here's the degrees Celsius equals, so we plug in 212. So 212 minus 32 degrees Fahrenheit. That's going to give us 180 degrees Fahrenheit. And then we have to multiply that times 5 degrees Celsius over 9 degrees Fahrenheit. Now, the 180 and the 9 can cancel out, and the degrees Fahrenheit. So 9 degrees Fahrenheit is a 1, and 180 degrees Fahrenheit divided by 9 gives us 20. So 20 times 5 is 100 degrees Celsius over 1. So the answer is 100 degrees Celsius. And we know that that's correct. Now, if we did it backwards, if we had the Celsius temperature and we wanted to find out how much that is in Fahrenheit, we use this formula. So 9 degrees Fahrenheit over 5 degrees Celsius times the temperature of the Celsius temperature, and then add 32 degrees Fahrenheit to it, and that will give us our answer. So 9 degrees Fahrenheit over 5 degrees Celsius, multiply that by our 100 degrees Celsius. 100 and the 5 can cancel out. So that's a 1, and 100 divided by 5 is 20. 20 times 9 is 180 down here. And then we add the 32. So 180 plus 32 is 212 degrees Fahrenheit. So you can try that out with a few other temperatures. You can do the 32 and the 0 and see if you can get it, or check any of these others and check it online with or a thermometer, and you can verify that you're right or not. So the metric system has another temperature scale in addition to the Celsius temperature scale, but this one is an absolute temperature scale, meaning that it contains absolute 0, which is absolutely the coldest possible temperature, theoretically anyway, that anything can be. So it's named after, the Kelvin scale is named after a man with the title Lord Kelvin. His other name was William Thomson. He was an Irish-Scottish physicist. And in 1848, he was able to calculate the lowest temperature possible to be negative 273.15 degrees Celsius. So at that temperature, atoms almost hold still, like they're always moving. But if it's negative 273.15 degrees Celsius or 0 Kelvin, they're holding as still as they possibly can. Now, one interesting, unique thing about the Kelvin scale is that we're used to writing the little degree symbol. So we say whatever degrees Celsius or whatever degrees Fahrenheit. But when you say a temperature that is on the Kelvin scale, you just say the number kelvins. So 0 kelvins, not 0 degrees Kelvin. There's no such thing to use the degree symbol. So something's 100 Kelvin or 350 kelvins or whatever. It's just no degrees. And you'll really love how easy it is to convert from Celsius to kelvins, or the Celsius or Kelvin temperatures to Celsius temperatures. So all we have to do is either add 273.15 or subtract 273.15. So over here, if we look at our Celsius thermometer, so here's 0 degrees, which water freezes at 0 degrees. If we want to convert that to Kelvin, then we add 273.15. So 0 degrees Celsius is 273.15 kelvins. And if we want to say, okay, well, 0 Kelvin is equal to what Celsius degree? equivalent. So then we would subtract 273.15, and it's equal to negative 273.15 Celsius. So easy peasy. Now, we're not going to be using the Kelvin scale right away, but definitely by chapter 5, we will be using temperatures on the Kelvin scale, because certain scientific mathematical equations, they just won't work if you plug in the numbers that are in Celsius temperatures. They have to have, they need to be the numbers that are on the Kelvin scale for the equations to work. Now, like I said earlier, we're mainly going to be just using the meters, the grams, and the liters, but here are a few more metric units. So SI stands for Systeme International, which is the same exact thing as the metric system. And the foot-pound second system, the only unit that they both share, that they both use the exact same thing, is the second. So in measuring time, time is in both systems is based on the second. So that's nice. We all know what a second is. However, you might not know scientifically what a second is. So did you know that 1 second is the amount of time that it takes for a cesium atom to vibrate 9,192,631,770 times? So if you have an atomic clock, or your cell phone probably is based on gets told whatever time it is based on an atomic clock somewhere. So they are based on they keep time according to a cesium atom. Now, 2 other things that we'll use in chemistry this year, just for a little while, is the joule. It is the SI unit for energy. A 60-watt light bulb is equal to 60 joules per second. And then also for pressure, measuring air pressure, we'll talk about pascals or kilopascals. So it's not the cute little Pascal from Rapunzel, but it's named after Blaise Pascal. And then over here, we've got volts, amperes, and watts. So these are 3 more metric units, but I don't think that we use them very much at all this year. It's just to know that they are metric units. So I think that's all that I have for this part of the section 1.2, and we'll talk about hopefully the rest of it all in the next lesson. So after you finish this lecture, please make sure you do quiz number 1, and you should be able to do quiz number 2 just from talking about all the safety things that we talked about before Friday on lecture 1. So if you weren't there on Friday, I'll be texting or I'll email you the quiz 1 and quiz 2, and if you could have both of them finished and turn them in on Friday, that would be great. So they're open book and open notes, but make sure it's your own work. All right, thank you. Bye.